All right.
All right. So I just want to welcome everybody to Season 1, Episode 2 of the Junkie Chunks. This week, we've got a very special guest with us, Mark Hanhardt from the Sanford Underground Research Facility in South Dakota, part of the, well, they do all kinds of experiments at Sanford. We're going to get into that a little bit, but we're going to kick it off tonight by talking about gravity waves, or gravitational waves. As always, I'm with me. My name is Dylan Walter. With me, I've got Tony and Justin. And for those of you watching for the first time, Mark Hanhardt is with us. Mark, why don't you tell us a little bit about yourself?
Yeah, no problem. Hi, everyone. Like you said, my name is Mark. I have a master's degree in physics, and I work at the Sanford Underground Research Facility. My background is mostly dark matter. I've recently made a switch to nuclear astrophysics, and that's what I work on mostly now. And I'm a PhD student while working at the lab, so this is the face of overworked.
That's excellent. Nice. So we talked. We've been talking for the last couple weeks, Justin, Tony, and I, about this amazing discovery or proof of Einstein's theory of where he predicted gravitational waves. What can you tell us about gravitational waves? What are they?
Well, that's a great question. It actually requires us to look at gravity in a whole new way. The real crux of Einstein's general theory of relativity was that gravity is no longer this force that attracts two bodies. That's the way Newton envisioned it. You know, the sun has a pull on the earth and the earth has a pull on the sun. Mm-hmm. He said that instead we have to envision the universe as this vast canvas, this space-time canvas on which mass, like the sun or the earth, they actually create deformations of this canvas. They create bend in space-time that allows matter to follow these bends in space-time. So, for instance, the classic example used is imagine a rubber sheet pulled taut. I don't know how you guys roll, but I have rubber sheets on my bed. So imagine rolling that or stretching that rather tautly.
Justin still uses rubber sheets.
Only on the weekends. Only on the weekends.
You know how to party hard.
Oh, wow.
But the idea is if you were to take a rubber sheet and stretch it out and place, say, a bowling ball in the middle of it, of course, that rubber sheet would bend in toward where that bowling ball is. Mm-hmm. And that's the same way that mass affects space-time. It creates a curve in space-time. So if I were to then, say, roll a tennis ball across that same sheet, instead of taking a straight line, it would, of course, veer toward the bowling ball because we've got an indentation in that sheet. And that's Einstein's general theory of relativity.
Like the things we drop the quarters in, and we watch the quarter go around and around. Okay.
It's exactly like that, yeah. So he made the break from, we got to stop envisioning gravity as this mutually attractive force, and instead imagine it as geometry. Is all it really is. It's a bend in space-time, just like that quarter machine. And that gives rise to the possibility that this space-time, this stuff, this canvas that the universe is painted on, it can have ripples in it. If I were to, say, drop a bowling ball in that rubber sheet, it would cause a ripple effect to carry out to the edge of that sheet. And that's really all gravity waves are. But we've looked for so long to find these gravity waves, knowing full well that they are incredibly, incredibly small perturbations in space-time. Einstein himself said they'd never be detected. So when we were able to see them with LIGO, we were able to both prove him right and prove him wrong.
And prove him wrong at the same time. That's awesome. Yeah. So
it's a good instance in which to be wrong, though.
Yeah.
It's a good instance in which to be wrong.
Oh, yeah, absolutely.
A measurable item to find in his theory. So
yeah.
So we did have a question. Connie asked, where does Mark go to school?
Oh, I should have mentioned that. I'm a PhD student at the School of Mines and Technology in Rapid City, South Dakota.
I'm not supposed to do this, but I need to step away a moment. I'll call right back in.
Right. So you go to School of Mines in Rapid City, South Dakota. Where exactly is that for people that are watching that aren't from South Dakota or have friends or family working at the lab?
Well, it's almost in the dead center of the United States, where Rapid City, I think, is about 50 miles from the geographical center of the 48 contiguous states. So we're about as Midwest as you can get. The lab in Lead is up in a little mountainous town about 25 miles away from Rapid City. 40 miles away from Rapid City.
Okay.
And that's where the school is.
So with this detection or with this discovery of gravitational waves, who was responsible for this discovery?
Okay, well that's the LIGO collaboration. LIGO stands for Laser Interferometry Gravitational Wave Observatory, and that's actually a collaboration of a lot of different universities. I think it's something around 1,000 scientists came together to actually make this experiment work, and it's been in the works since the 80s. I think it's been running really, at least nominally in some form, since '94. And it's all these scientists who work together who were able to actually collect the data from the two LIGO observatories in Washington State and in Louisiana. I can't remember the town it's in. They're the ones who collected the data that allowed us to actually make the final call that, yes, these are, in fact, gravity waves. We have definite proof.
So 2 sites. Why 2 sites?
Well, you've got a lot of problems with trusting just one site. There are any number of noise signals that could look a little bit like a gravity wave. And it's worth mentioning that the LIGO detectors are the single most sensitive measurement devices mankind has ever made in any regard.
Wow.
And they're very sensitive to really any sort of noise that could come up. So a car driving 10 miles away from the LIGO detectors can set off the detector. They can actually create a measurable effect. Wow. So when you have just one detector running, you've always got random noise that it wouldn't necessarily look like a gravity wave, but there's always the chance that it could be mistaken for one. If you have 2, however, you're able to look for a coincidence between the 2. It's very, very unlikely that you'll have 2 random effects that look like gravity waves happening at both sites at once. Whereas if we have a gravity wave, you will definitely see them at both sides at once. And that's exactly what they saw.
So the devices that detect these, the interferometers, right? You said they're the most sophisticated measuring devices ever created by mankind. The wave that they detected, and you can correct me if I'm wrong, but is it true that was 1/1000th the width of a proton? That it was that?
Yeah, and that's their level of sensitivity. They had just recently, as I understand it, just upgraded some of their detectors from the original LIGO detectors to what they're calling advanced LIGO detectors. And it was just 2 days after that they actually received these waves. And you're exactly right. It's to a level that's 1/1000th the width of a proton. And that, to give some idea of that level of precision, the same ratio would be measuring the distance between here and our closest star, which is Proxima Centauri, with an error of it's measuring that distance and then being able to differentiate the width of a human hair. That's how small the distance in that change of the laser wavelength they were able to detect. So it's the single most sensitive measurement device we've ever built.
So let me ask you this, because a lot of people that participate in watching things like this, myself included, Tony and Justin, I'm sure would fall into this category. We don't necessarily we don't understand why the research needs to be done, right? So what?
Agreed.
Yeah, what are the practical applications of this discovery? And I know that the science, when we talk about relativity and things along that nature, that's how we get GPS in our cell phones, right? That's how we get satellites in space and things along that nature. But what is this gonna do? How does this help similarly to that?
Hopefully you're talking about warp technology.
Well, it could be. The thing is, we don't know yet. We understand gravity waves pretty well mathematically, but as far as they actually interact with the universe, we're still learning a lot. So we're taking the baby steps into
So
this
does
kind
that
of
mean
science.
over the next 50 years you guys get to play with them now?
Yeah, it really does. And that's exciting for us in a nerdy sense, of course, because we actually get to look at the universe in a totally different way. We've looked at it for, several thousand years in visible light, and we've looked at it for the past 50 years in radio waves and gamma waves. Now we have a chance to actually look at the universe to see what it looks like in gravity waves, and we can learn so much about the way the universe actually formed in the first place and what's in the dark parts of the sky. We can't see anything else. So yeah, we get to play with them for a while and actually see, what we can learn from them, and one day what we can do with them.
Okay.
That's awesome. So what makes these so sensitive, and how were they able to? I mean, I know they use lasers and mirrors, right? That's pretty much what these interferometers are. Is that right?
Yes.
We look at stuff like the Hubble Space Telescope, and soon I think it's the Webb Space Telescope is going to be going up. What makes these mirrors so special?
Well, it's first of all the accuracy with which they're able to determine the distance between the source of the laser and the end of the mirror. But the basic technology is that they take one laser beam and they shoot it through a laser splitter, a beam splitter. So you've essentially got one beam of light that's separated into two, and those two waves travel at a 90-degree angle. I suppose I should go like this. They travel at 90 degrees to each other. One goes 4 kilometers to a mirror straight up, or straight forward, I suppose, and bounces back, and the other one goes 4 kilometers to the left and bounces back. And when they return at that beam splitter, the beams are combined again. And if everything is working perfectly, they combine in such a way that they deconstructively interfere. They actually, the two waves of these laser pulses cancel each other out. So when everything's working fine in the LIGO detector, you don't see anything. But when a gravity wave goes through this 90-degree angle that I mentioned before, it actually stretches out one of those sides while it compresses the other, and then it does exactly the opposite. It then compresses one side and shrinks and lengthens the other, and that changes the way the recombination of those two light pulses happens. So suddenly, where we saw nothing because these two light
now you see something.
Yeah, we suddenly see a tiny signal that indicates they're not deconstructively interfering exactly the way they were before. So something has happened. And when we see it in two detectors at once that are half a country apart, we know.
How long did it take for somebody to think tank the idea of splitting lasers and then bringing them back together? That's just amazing.
Well, believe it or not, the idea is more than 100 years old.
Okay.
It's a variation of something called a Michelson-Morley experiment. This is actually the same technology that was originally used to measure the speed of light in the first place. Of course, they didn't have lasers. They had highly coherent beams of light, but they didn't have lasers yet. But it's basically the same idea they were using, but much, much greater accuracy.
Okay.
So one of our viewers said it disproved the ether.
The Michelson-Morley experiment, it would have even been 120 years ago. That was originally designed to not only measure the speed of light, but to prove that light was the same speed no matter what direction you pointed it in. Okay. An original theory was that the entire universe is filled with this ether, this imaginary substance that actually let light travel through it. And since Earth was always moving, we should be experiencing this ethereal wind. And if that ethereal wind was correct, then light would travel at different speeds depending on which direction you pointed it. So that's why they built it in the first place. Yeah.
Very cool.
So you every now and then hear someone use the phrase "into the ether." This is what they're referring to. This primordial, no longer accepted idea.
Gotcha.
Yeah.
So does another, and we're going to ask one more question from our viewers. Does LIGO use PMTs?
Ooh, some background for anyone who's not in the know. PMT stands for photomultiplier tube. It's a device we use for really, really sensitive light detection. You can actually pick up a single photon, the smallest quantum packet of light the universe can produce. You could pick that up with a PMT. And we use that in a lot of different physics experiments, including several at Sanford Lab. As far as I am aware, LIGO doesn't use them, but I'm not that familiar with their detector. I think they use something else for actually interpreting their photon signal, but I couldn't promise. But I don't believe they use PMTs.
Okay. So how big were these? Because these were two black holes that they believe there were two black holes that collided to cause this event.
Yes.
How big were these black holes?
Let's see. One of them was 29 solar masses, so that's 29 times the mass of our own sun, which to give you scale is big. The other one was, if I recall, 36 solar masses. So these are two objects that have more mass than our entire solar system, nearly 50 times over.
Wow.
And then they're in an area so small, you could fit them within, South Dakota. Yeah. It's amazing the level of stuff you deal with in cosmology and astronomy. But what's so amazing is that these massive and very large objects were orbiting each other at a rate of several thousand times a second. They were accelerating they were traveling rather at nearly half the speed of light when they finally collided. And that's a lot of energy, as you can imagine, because that's a lot of mass and that's a lot of speed. When they collided, they created gravitational waves so energetic that it carried away 3 solar masses of pure energy in gravitational waves, and that's what we actually detected. But for that single instant, for that microsecond, when they were merging, those merging black holes emitted more power, 50 times more power, if I recall, than all of the other stars, the entire visible universe at that time. So we're talking about big numbers here.
Big numbers. Really big numbers. How far away was this?
1.3 billion years is what I've read. So 1.3 billion light years, rather, away. And because gravity waves travel at the speed of light, it means it also happened 1.3 billion years ago.
How far are you guys capable of detecting an event like this?
Well, that's something we're still feeling out because, of course, these are the first gravity waves we've ever detected. Now, theoretically, if it were massive enough, we could detect them out to the very edge of the visible universe. But it would have to be an incredibly, incredibly energetic event to create the kind of gravity waves we could see there. The problem is, just like a street lamp it's 4 times as hard to see if you go 2 times as far away. You've got this inverse relationship, inverse square law. We have the same kind of relationship with gravity waves. If something is twice as far away, it's 4 times less powerful. In fact, in gravity waves, I think it might be quite a bit more. But my point is, as things get further away, they get exponentially less powerful for us to see. So ultimately, 1.3 billion years is pretty far away.
Right.
I would like to see stuff closer, of course, but it's hard for me to put a limit on it because this is the first one we've seen.
Okay.
That's unbelievable. I mean, you know, when I first started talking about this topic with the other chunks here, we were like, we read something on science.com, we read something on this, on that. We got we get Sanford's Deep Thoughts newsletter as well. So we read that and we thought, oh yeah, we can talk about this all day. Oh yeah, we can do that. And with what we've been learning over the last week while we were preparing to do this show, we realized how little we knew about anything related to this whatsoever.
That's the physics experience. I have that every day.
Man.
So you had you said that there are 1,000 people collaborating with LIGO.
Yeah.
And I know that there's another group that's part of that, the Virgo group. Helped author this paper. As
I understand it, I've not studied their structure too much, so I couldn't tell you much more than that.
Okay.
But yeah, it's not uncommon for these very big experiments to have a lot of scientists involved because there are a lot of subsystems that you have to get working, and they take place over 30, even 35, 40 years. So it's not unusual to have a whole bunch of scientists involved in it. This has been dubbed the collaborative age of physics experiments. It's not very often that you have a single person experiment that really reveals something big about the universe anymore. And this is a great example of it because it's a huge collaboration, but they also discovered something just revolutionary.
That's absolutely incredible. Connie wrote a question over here.
Questions.
Tony, you want to go ahead and take it?
Well, there's a couple that I feel combined together to help explain what we've got. A couple questions here. The first would be, how many gravitational wave detectors are there around the world? Also, the secondary one would be, how are you guys able to do basically detect a gravitational wave? If you would explain that one to us again, based on the separate stations.
Okay. Well, for the first part, I actually don't know how many experiments there are. I know there's at least half a dozen. There could be as many as a dozen more experiments that are looking for gravity waves. And there's a bunch of different technologies that people are using. One involves what's called if memory serves, it's called a Weber bar, which is it's just an inert chunk of metal, and it's actually not much more complicated than that. The idea is that if you have a chunk of metal sitting in a room with no vibration whatsoever, you isolate that from any sort of outside force as much as possible, then the only way it could ever start vibrating on its own is if it picked up a gravitational wave that just happened to be at the resonant frequency of this chunk of metal. And there's a lot of experiments out there that use that or a variation of that, and no one's ever detected anything. There have been some reports of something detected with that, but none of them have ever been proven. And that's probably due to the fact that you'd have to have a gravity wave that was pretty powerful, first of all, to do that. And then it would also have to be of a very specific frequency in order to set off that Weber bar. So that's some of the experiments. The only experiments that I've actually studied up on, the ones I'm actually familiar with, are the interferometry, like the LIGO projects. And the way those work is really just by detecting. It boils down to this: you've got a measuring arm this way, and then another measuring arm at 90 degrees to that. And you're really just looking for any variation in the measurement on this side compared to the measurement on this side. And that's at the basic heart of the project. That's all that we're looking for with a gravity wave, because a gravity wave has this unique property that when it travels through stuff, it stretches and compresses. If you were looking at, for instance, a circle that were being stretched and compressed by a gravity wave, it would do this very slightly. It would squeeze and compress and squeeze and compress.
Okay.
This is greatly exaggerated, of course. You wouldn't have this kind of movement.
Yes.
It would be on the length scale of 1,000th of a proton diameter, but it'd be that kind of geometric look. So all we're really doing is using this incredibly sensitive laser ruler, really, to detect if there's any change in the length of each side. And as a wave goes through that, it should compress this side and lengthen this side out, and then compress this side and lengthen this side out, and over again. And by picking up the oscillation, by using the splitting and recombination of laser waves, which is really just a technical detail that means we're measuring the length of that arm, we can tell if we're looking at a gravity wave or something else.
Right.
That's awesome.
The way I tried to answer the question earlier was you have a second station in another area in the country, and you guys compare your results together to see if that's actually gravitational wave or just like you said earlier, a car passing by, that kind of thing.
Yeah, because there's a lot of things that could set off your detector. Yeah.
Cool.
So let me ask you this, because we talked a little bit about LIGO, and I mentioned Virgo, which none of us know anything about, but that's we were told was part of the collaboration. What are you guys doing at Sanford to do anything with gravitational waves?
Well, we're not directly related, or we're not directly involved, rather, with LIGO, but we're exceptionally excited at Sanford Lab for the LIGO results, because it actually sets the stage for something we've been working on for a long time. We have an experimental group underground called DOUGLE, which, if I recall, stands for Deep Underground Gravitational Lab. I think that's right. Mm-hmm. And basically, they're studying the underground environment to see if it would be suitable for a LIGO-type experiment, because and this is the logic behind it, and this is also what preliminary results seem to indicate is true. The idea is underground is a much better environment to run a LIGO-type experiment, because there's a lot of variables on the surface world that you can't control that mess with experiments like LIGO. There's atmospheric concerns. Cosmic ray concerns are always a problem. But more than that, you have uncontrollable temperature and humidity on the surface, because you're at the whim of the weather. And there's actually, this seems counterintuitive, but seismic activity is easier to handle underground than it is on the surface world, because on the surface world, you're at this boundary of the Earth and the sky, and Earth doesn't react the way you think it would when it shakes around. Even when it's a really, really small shaking around, like, for instance, a car driving by, Earth kind of jiggles in a way that's hard to predict and therefore hard to account for in your experiment. Whereas when you're underground, everything shakes together. So wherever your LIGO is, it stays together. It stays stable. There's a lot of other things, like being able to keep radio waves away because you're blocked by a mile of rock over your head. And you're able to control access, so you don't have someone just walking by. You don't have people driving by as often because the nearest road is a mile above your head. So there's a lot of reasons why underground would make this type of experiment more successful. So now that LIGO has actually discovered, has proven these gravity waves, the next generation of astronomers are going to build telescopes looking for gravity waves, and they have to build them more sensitive than LIGO is, and underground is exactly the place you want to do that.
Wow.
So we're excited that DOUGLE is already laying the groundwork for this.
And So how deep is the Dougal experiment? What level is that in your lab?
Well, actually, it spans quite a few levels. I think it runs all the way from now. Our Sanford Lab runs from, of course, the surface all the way down to about a 5,000 foot level below the surface of the Earth. There are also levels another 3,000 feet below that. They're currently submerged in water, and they're not useful for science. But we currently have these seismometers that are taking seismic data for Dougal everywhere from, I believe, the 800-foot level down to the 4,850 level. So that's about 4,000 feet right there. And then they actually run another kilometer and a half out to the side. So in all, you actually have a cubic mile, essentially, an entire 3D volume, cubic mile, that is outfitted with these sensors, and that's the area they're actually looking for all this seismic data.
Wow.
Is there anything about your location that makes it particularly useful for your data gathering, like the buildup of the rock or anything like that?
Yeah, actually, there's a few things that make it really useful, not just for Dougal, but for the other experiments we have underground as well. Number one is the fact that we're in a really seismically quiet part of the country. There isn't a fault line within 2,000 miles of us, and there's not a lot of seismic activity that happens around here. I'm given to understand, and geology is not my field, but I'm given to understand that the geology of the Black Hills, which is where Sanford Lab is located, is unique in that rather than the hills forming by two tectonic plates coming together and pushing up, instead the whole area was crust that lava intrusion just pushed up, and that's formed the entire hills here. I've been told this is the only place on Earth where that specific type of intrusion has happened, and that apparently lends special properties to the rock around here structurally, of course, making it very sound. But on top of that, the type of rock that we're in at Sanford Lab is particularly quiet, radioactively speaking. Most rock everywhere else in the world is going to have a lot of uranium, a lot of thorium, and a touch of potassium in it, and that's radioactive. And when you have experiments that are very, very sensitive to radioactivity, that's a problem. And here we have certain rocks that have those high concentrations, but we've built the labs in sections where they don't. So that's what makes it particularly useful for us.
Sure. Question that we just got is, do you know what particular kind of rock it is? I'm
afraid I don't. I've been told, but astrophysicists, so in one ear and out the other. Yeah. We have geologists who can tell you just from the taste of a rock exactly what area it came from. That's beyond my ability.
You guys should get those geologists out from underground if they're eating rocks. I mean, that's a bit ridiculous.
Well, it's apparently a good way to detect the exact chemical structure of a rock. I'm not defending it, but that's what they tell me.
Fair enough. So we had talked a little bit earlier about what the practical application for this experiment or for this discovery is. How about, when you said 50 years from now or later to really be able to take full advantage of it, what are they hoping to do specifically with this? You said we get to play with gravity waves later, and Tony made a joke about, it better be something like warp drive. But in all seriousness, what because we talked that this is possibly going to create an entirely new field in science, right? So what could this do for us?
Well, on the practical side of it, it's one of those things where it's difficult to say. Looking back, we have scientists like Ernest Rutherford and J.J. Thomson who worked for years on the electron, not understanding what the electron was or what it would be useful for. And of course, it was their work that led to our modern world. Everything we have now runs on electricity, and we wouldn't have been able to do it without their work. So we may be in a similar situation like that. We don't really understand the fullness of what gravity waves could be used for. But I can tell you the first inklings we get are, of course, that astronomy, first of all, is the first use. Within the next 50 years, I would expect us to harness gravity waves as a way to look into the universe, and in particular to look at the Big Bang, to understand how the Big Bang took place, how it created everything around us. Because traditional methods where we look at visible light, where we look at microwaves, where we look at gamma rays and radio waves, those can only look so far back in the history of the universe. And we get to a point where 380,000 years after the Big Bang, we can't look any further back than that, because the universe was entirely opaque to this electromagnetic radiation. But with gravity waves, we should be able to look back to the very instant the universe was born. We just have to devise a way to actually pick up that type of quiet signal. On top of that, and this is pure science fiction that has some mathematical backing to it, say 500 years down the road, the ability to understand gravity waves, which are in essence ripples in space-time, may give us the basis for understanding how to manipulate that space-time ourselves. If we're ever going to achieve wormholes or faster than speed of light travel, if we're ever going to do those things, and I'm not saying that they are possible, I really hope they are, but if they are possible, we're never going to do them without a firm and complete understanding of gravity waves. So it may not lead to that eventually, but there's no way we can get that without doing this work first.
Right.
So that's really long term. But for the next 50 years, I expect astronomy will be the main focus of gravity waves.
Wow.
So with the detectors that they have at those two stations, the event was detected. They believe that it came from the southern hemisphere. Is that correct?
Yes.
And how do they know that? How do they figure that out?
There's a 7 millisecond difference, if I recall, between when the detector in Louisiana picked up that oscillation and when the detector in Washington State picked up that oscillation. And if I'm not mistaken, the travel distance between Louisiana and Washington at the speed of light is 7 milliseconds. So if you've received it at this one first and this one second, it had to have come this direction.
Gotcha. So
it had to have been south. It's not a very clear direction, because that's as what's the word I'm looking for? That's as precise as we can get. It's south of Louisiana. It came from that direction. That's a whole hemisphere, admittedly, but that's impressive information that tells us quite a bit of stuff, because that's also the direction of really the bulk of our galaxy. Because we on the northern hemisphere, we're looking out toward the empty space outside our galaxy. In the southern hemisphere, they're looking into the core of our galaxy. And that means that this gravity wave, which was 1.3 billion light years away, which is well beyond our galaxy.
Very cool.
It traveled through all the matter in our galaxy and got to us undistorted.
And we still picked it up.
Yeah. And that's the amazing thing about gravity waves. They can travel through anything, really, and not be distorted. And light doesn't do that. So that's why this is so useful for astronomy. It can see through stuff, essentially.
That's crazy. That's great. I'm still stuck on the 1,000th the width of a proton. That's just impressive.
Yeah, that's incredible. That is precision engineering.
Yeah.
One thing's when they're looking upwards to space that we're dealing in light years and bigger numbers, and then we talk about a number this small, and I mean it's crazy that it has the whole spectrum of measurements going through it all the time. Yeah, that's just baffling.
Well, that's modern astronomy for you. We have to bridge the scale from the biggest to the very, very smallest. It's an exciting time to be involved in the field, really.
Yeah, and there's just when you think about this as an event, you're kind of thinking, wow, this is when thinking about two what were they're classified as heavy black holes? Was that correct?
I think so.
When you think about things that large hitting each other, that's a terrifying thought, right?
Yeah, absolutely.
So how
we
far?
get this amazing result from it.
How far away would you want to be if that happened?
Ideally, 1.3 billion light years. Well, to give you an idea of the power here, let's talk nuclear weapons for a second. You guys are familiar with the atomic bombs that were dropped during World War II. These are massively inefficient bombs, but they essentially follow Einstein's equation E equals mc squared. The energy we got out was the mass times the speed of light squared. And that's an equation we use in a lot of different fields in physics. The mass that was actually converted into energy that created the massive explosions that wiped out Hiroshima and Nagasaki, that was a minuscule amount of matter. That was an amount of matter on an atomic scale, just a handful, really, of atoms worth of mass converted into energy was that big explosion.
Wow.
So try to reel in how massive that, or how incredibly large those explosions are for a microscopic, and I mean literally microscopic, invisible to the naked eye amount of mass. Now these black holes, when they collided, they converted 3 solar masses worth of mass, so 3 suns worth of mass into pure energy in that instant. I can't imagine being anywhere near that thing and not being completely destroyed.
Wow.
Fortunately, the energy was turned into gravitational waves, and gravitational waves are themselves not particularly destructive, but the accompanying whatever else would have been released in that collision would have been devastating. So I'm almost uncomfortable with 1.3 billion light years.
Right.
So I have a question just based on your explanation then. Are there any other readings we picked up from the collision of these 2 black holes other than the gravitational waves?
I'm not sure.
Okay.
I'd love to make up an answer, but I really don't know. I've begun to hear some whispers, and I've looked at some results online suggesting that they might have seen a coincidence. Something else that may have happened at the same time, but I couldn't verify anything, and I don't know any of it well enough to put it out there without checking it. But I would expect us to see something. I just don't know if we
have a pretty good friend from the blabs that we've participated in just joining us and asked a question. Are we able to measure the gravitational waves created by the Big Bang?
But that's what I was talking about before. The gravitational waves that would have been created at the very instant of creation, at that very instant that the Big Bang went off. We haven't seen them yet. We would like to, because that would tell us so much more about this missing 380,000 years, the beginning of the universe. I expect we should be able to. But we haven't yet, and I don't know, at least currently, of any coherent theory for what it would look like.
And then another question was, do they bounce around or just pass us by and go off forever into space?
They just go on forever. The odd thing about gravity waves is, they're not unlike water waves interacting with other water waves. If you've ever had if you've ever seen 2 water waves interact with each other, they really don't. They pass through each other and just keep going. Gravity waves are pretty much the same way, and they don't interact with normal matter, the Earth, the sun, you and me, the way we expect normal matter waves, water waves, for instance, to interact with us. There's not a lot of sloshing. There's not a lot of bouncing around. In fact, right now, I don't know of anything except deep gravitational wells that interfere with those waves at all. So that's what makes them so incredible. I'm sorry?
What do you mean when you say that, deep gravitational wells?
Black holes, for instance, could probably cause some some distortion of a gravity wave. My general relativity, I'll admit, is not good enough for me to actually do a calculation on the fly to tell you what that distortion would look like. I expect there would be some sort of distortion, but what makes gravity waves so valuable to astronomy is the fact that they are so hard to distort. A gravity wave that we see from 1.3 billion light years away, even though it's traveled through countless galaxies and the core of our own galaxy to get to us, has remained essentially unchanged. That's incredibly useful for us.
So this was, you said 29 times. The first one was about 29 solar masses.
Oh, yeah.
For the one black hole, and the other one was something like 30 or 34, you
36,
said? Is that right?
yeah.
36 solar masses. So to put that in comparison, how big is the black hole at the center of our galaxy?
I've seen a lot of figures on that, and I couldn't tell you what the final value is, but it's several thousand, and quite likely, quite probable, several million solar masses.
Wow.
Yeah, well, it's
that there's no chance that has a pair sitting anywhere near it, right?
Well, it actually has quite a bit of stuff orbiting around it, and there's no guarantee that some of the stuff orbiting around it isn't black holes. In fact, I fully expect it would be. Okay. I think the chances are very, very small if the black hole would be of a similar mass. The collision that we saw the gravitational waves from, this 29 solar mass and this 36 solar mass, the gravitational waves were so large because they were so close in mass. Had there been a much more uneven distribution, the math wouldn't have worked out, and the gravitational waves would have been much, much smaller. If we had these two black holes at the center of our galaxy, millions of solar masses encircling, I expect we would have detected that first.
Okay.
So there was another question from a viewer. Do gravitational waves provide any insight to what gravity is, maybe as a particle?
Yes, absolutely. I'm afraid I can't speak in much depth on that because it's a little beyond what I've studied. I've studied general relativity really on the surface. But absolutely, anything else we can learn about the way that gravity propagates through space helps us understand what it is. And this is a really a sticky problem for physicists because we have a really good grasp on the other three fundamental forces in the universe, which are the electromagnetic force, the weak nuclear force, and the strong nuclear force. We have a really good understanding of how those work, how they propagate through space, and in particular what we call the gauge bosons, the particles that are associated with them that actually transmit force across space. We have a really good understanding of that, but gravity, we've got a blank. We don't understand it very well at all, and some of us are holding out hope that we will discover a gauge boson, a particle that transmits the force called a graviton. But it's so incredibly hard to study gravity because it's so many orders of magnitude weaker than the other forces, and it seems to play by its own rules. So yes, anything we can get on gravity waves will help us understand gravity and what it's made of and why it's so elusive to physicists. So
is that where like astrophysicists would have to depend on particle physicists to really help with that? Because you had mentioned finding that missing particle.
Yes, absolutely, and we're reaching an age now where astrophysicists have to be well versed in particle physics. Again, my field is nuclear astrophysics. I have to understand nuclear physics and astrophysics. So the smallest scales and the largest scales at the same time, because you can't look out there and understand what's going on without looking within and understanding what's going on. That sounded way more spiritual than it did in my head. But you can't understand what's out there without understanding what's in here first.
So one of the other questions that just came out was what kind of information would be gained from witnessing two neutron stars colliding that we would not be able to find from those two colliding black holes, if any, vis-a-vis gravitational waves?
Well, it would be interesting to see two neutron stars collide. I should start by saying there's not a huge difference between the two, because neutron stars are also very massive bodies, and they can rotate roughly the same speed, and they can impact, and they could create gravitational waves that are nearly identical to the ones we saw from these two colliding black holes. The one difference would be that because they're not black holes, they wouldn't absorb all of the radiation that's created in that collision, all of the X-rays, all of the neutrinos, all of the other signals. So if we were to see two neutron stars collide in the same way these black holes did, we would see the same thing gravitational waves wise, but we would also see all this other additional information in neutrinos, in X-rays, in gamma rays, and then correlating that back to the gravity waves, it would open up a whole new world of information for us, because then we'd understand the part of physics we do get, the electromagnetic stuff, and be able to, correlate it with the gravitational part, the part that we're having trouble with. So it would be incredibly useful.
So to follow up with that, the question about neutron stars, when we're talking about the mass of a neutron star, it's nowhere near the mass of these black holes that collided, correct?
No, not. I mean, they're not quite as massive. I'd have to go back and actually look at the mass range of neutron stars, but some of them can get incredibly massive.
Okay.
I'm thinking on the scale of 10 to 20 solar masses at the very least.
Oh wow. Okay.
Yeah. So some of those neutron stars are big.
And we were talking with we had talked with a member of the LIGO team a couple days ago, and he had said that for a neutron star to be able to detect, let's say, two neutron stars of similar mass were to collide, he said that he believed that their equipment would only be able to see about they would only be able to detect that from about 100 million light years away. And I'm sorry.
Oh no, I'm just listening to you. That could well be because the masses are different. It's entirely possible that I'm wrong about the mass limits of neutron stars. That's a field I'll admit that I've been dark matter for years, and I've only recently made the change to nuclear astrophysics. So I'm not up on the knowledge I really need in that field yet. I could be wrong about the masses, but the interaction would be much less powerful. So
right. Okay.
Closer for us to see it. Yeah.
Yeah. That was my question. I was because you had mentioned that when they collide, you can detect so many different things because it's a visible collision, right?
Yes.
So you can see it in all the different ways. So would you guys rather see gravitational waves from things like neutron stars then, so that you can measure it much differently than you would be able to with the black holes, since there's no visible light, or most things aren't visible that are emitted from the collision?
It depends on who you ask, because a lot of different physicists have a lot of different goals. For what interests me personally, yes, I would rather see the neutron star collision. I think that would be much more interesting because that correlation of data is much more interesting to what I want to find out. Whereas the collision of black holes gives us similar but slightly different information about, well, first of all, the internal structure of black holes, which is baffling in its own right. So it's different information, and it depends on what type of physicist you're talking about. We all want to see different stuff.
So we want to see it all collide. We just want it to be far away.
Yeah,
right?
That's
like
basically
earlier.
Yeah. Scientists love
restrained chaos.
Yeah,
not local chaos.
Get rid of that fuzzy math at a distance. Another question that came through was, what is the current quantum field theory of gravity?
Ooh.
And if you can answer that without a chalkboard and a bunch of graphs.
I think you're impressing everybody with how digestible you're speaking.
Oh, I hope so.
They're asking the hard ones.
Well, It's a trick question, because the truth is you could get a quantum field theorist in here and he still wouldn't know. And that's the thing about quantum gravity. It's so hard to digest that there's probably 3 people on Earth who have a really solid idea of what's going on in quantum gravity right now, and they're all in an asylum somewhere. It's a really difficult field to actually grasp, and the problem comes because gravity, as we understand it, is essentially general relativity. Everything we know about gravity comes from Einstein's theory of general relativity, and quantum is a completely different set of theories, and you can't put them together. When you try, the math doesn't work. You end up getting a lot of division by zero equations, and obviously that's a problem. So that's why we have difficulty understanding stuff like black holes. We understand quantum systems. We can study quantum systems in the lab, and we understand gravity on a large scale in the universe. But when those two things come together, which is a very, very small thing like a black hole, which is infinitely small, interacting with space-time, which is general relativity and is very big, when those two things interact, our math doesn't make sense anymore. So there's a big push in physics to understand gravity better and to understand quantum better and try to come up with a way to merge these two fields. It's not one that I follow, but it's one that I know has met with a lot of difficulty. And the current state, if that's what the question was, the current state of the field is confusing. And I suspect that will be the same for a while.
So we're gonna have the one more question, and then we want to kind of pivot to another topic here.
Okay.
And the question is, are there any possible applications for placing limits on dark matter via gravitational wave measurements, such as macho detection?
Well, I'll tell you what, most of that question makes sense to me, except for the macho detection part. Are there any possible applications of placing limits in dark matter via gravitational wave, such as machos? Oh, I see what's going on there. Okay. To give some background here, machos, to start with, are a theory about dark matter. So dark matter is this idea that there's a lot of mass in the universe that's affecting the way galaxies form and the way they move, and we just don't know what it is. We don't see it. It's not emitting light. Machos is a theory. It stands for massive, compact halo objects. And the idea is that the universe is filled with these massive, compact halo objects. So those are objects like Jupiter that have a lot of mass in them, but they don't actually emit light. So the idea is that there's Jupiters everywhere out in space, and they're causing all these gravitational anomalies, but we can't see them, obviously, because they're not emitting light. And it's a theory that ultimately lost favor in the 80s because as we study stuff like the Big Bang, we study cosmic microwave background from the Big Bang, we're able to put a limit on how much mass was actually, normal mass was created in that Big Bang, and it rules out machos. Machos can't exist, at least not in the number to explain dark matter, because the Big Bang theory won't allow it. And I think that's what he's asking. Is there any possible applications for placing limits on dark matter via gravitational wave measurements? Absolutely. Because gravity waves, if we understand them better, if we're able to detect more of them, we'll understand the Big Bang better. And if we understand the Big Bang better, we'll understand everything that was ever created in the universe, including dark matter. We'll be able to put an upper limit on how much dark matter was ever created. So, yes. There are applications for that. It's convoluted. It'll take us a while to get that data, but absolutely, and that's one of the big things I'm looking forward to as a dark matter enthusiast.
So you mentioned dark matter, and the last question it asked about dark matter, and that's kind of how we want to we kind of want to pivot.
Transition.
Transition. A great opportunity. So for the viewers watching and typing in your questions, I appreciate it. Why don't you tell us a little bit about what you do specifically at Sanford and the work that you're working on?
Okay, I'd be glad to. I love talking about me. I honestly have, I think, the greatest job in the world because you guys probably haven't picked up on it because I'm pretty good at hiding it, but I'm a bit of a nerd. and I enjoy
I
science.
didn't get you on to that either.
Yeah, well,
Welcome to the club.
well, I have a job where I'm an experiment support scientist at Sanford Lab, and that really means that I get to help wherever I'm needed on any of the projects that are going on underground. We have 22 active projects going on underground right now in physics, which is my field, but also biology, geology, chemistry, and engineering. And we really run the gamut. And I get hands-on with really any experiment that happens to need help that day. And that's really a lot of fun for me. I've spent most of my time on something called the LUX dark matter detector. LUX is LUX. It stands for Large Underground Xenon, and that's a dark matter detector. The scientists of LUX suspect that this dark matter that we were just talking about previously, it exists in a form that we call WIMPs, which is in opposition to the previous theory we called machos. So, WIMPs versus machos there. But the basic idea is that the universe is filled with these subatomic particles that are invisible, and they're also intangible. So the room you guys are sitting in, well, the 3 separate rooms you guys are sitting in right now are probably filled with these WIMPs, and they're passing through your body and your walls, and you're never noticing them because they are invisible and intangible. And LUX is looking for those particular particles in order to understand, what makes up this dark matter component of the universe. And that's very important because this dark matter, whatever it is, whatever it's made of, and again, we hope it's made of these WIMPs, but whatever it's made of, there's 5 to 8 times more of all that stuff out there than all the other matter. So, you count up you and me and the Earth and the sun and all the stars in all the galaxies out there. That's just 20% at the most of all the actual matter that's in the universe. The rest of it's this dark matter stuff. So I get to work on LUX, which has been an absolute blast for the past few years. I also get to help on a project called Majorana, the Majorana demonstrator, which is involved with neutrinos. Neutrinos are these incredibly small, almost massless particles that are created in great abundance in the sun and really any other nuclear reaction. And these neutrinos, we don't understand much about them, but we're still, we're trying to learn quite a bit more because there's a lot of neutrinos in the universe. They are everywhere, and just like the WIMPs, the room you're in right now is filled with neutrinos coming from the upper atmosphere and coming from the sun. And the thing about these neutrinos is that they are, again, intangible particles. A neutrino can pass through a chunk of 100,000 light years side to side and only have a 50% chance of actually getting stopped by that chunk of lead. So they travel through a lot of stuff.
Wow.
And the really interesting thing, at least from a particle physics standpoint, is that neutrinos could be their own antiparticles. So neutrinos could annihilate with themselves. And if that's the case, that would explain why our universe has so much matter and so very little antimatter, because everything we understand about the Big Bang suggests they should have been created in equal amounts, and then they should have just annihilated. We shouldn't be here. There shouldn't be matter or antimatter in the universe. It should have all canceled out. So the Majorana demonstrator is looking for a rare type of nuclear decay called neutrinoless double beta decay, which would prove that neutrinos are their own antiparticles. So that's another one of the projects I get to work on, and I feel like I'm going long here. I'll just talk about 1 or 2 more, even though we have 22
can we ask
active projects.
We've got a couple questions here. One is what are neutrinos for? What are they? I'm assuming they mean what are they? What are neutrinos, or what do they do? Or
well, it's tough to answer because we're still learning so much about them. But neutrinos they're nearly ubiquitous. They are everywhere. I think the stats are if you were to hold out your hand in the room you're in right now, 100 trillion of them will pass through your fingernail in a second. They're that numerous.
Wow.
They are everywhere. And because they make up such a big part of, the matter in the universe, it's important for us to understand them. As far as what they do and what they're used for, we're still trying to learn what they do. We're not currently using them for anything except possibly learning. Well, you know what? I take that back. We are using them for quite a bit because by detecting neutrinos, by detecting neutrinos, we actually can understand the nuclear fusion that's happening inside the sun. And that's kind of hard to find any other way, because you can't see into the center of the sun, obviously, because there's a big bright cover on the sun. The corona is shining, right, and we can't see past that. Neutrinos, however, pass straight through stuff. So if we look at just the neutrinos coming from the sun, we can see exactly what's happening in the center of the sun.
And are neutrinos do they only come from the sun? Or from
No,
stars?
They actually come from a lot of different processes. The sun is the strongest source around us, but neutrinos can come from nuclear decay in just the Earth around us. They actually come from nuclear decay in the human body. That's something we don't think about a lot, but the human body is fantastically radioactive. And neutrinos, actually, they come from nuclear reactors, which is really important because a neutrino signal coming from a nuclear reactor that's generating energy is slightly different from the energy coming from a nuclear reactor that's being used to create weapons-grade material.
Really?
So we're actually able to use, from a national defense point of view, we can actually set up a neutrino detector and find out if a country is actually creating weapons-grade material.
Wow.
That's impressive.
It's pretty neat stuff to be involved in. On top of that, neutrinos are fantastically useful for understanding supernovae, rather. When a supernova explodes, the neutrinos that are created in that nuclear explosion, they arrive just ahead of the light that's created in a supernova explosion. So when we get a neutrino signal on Earth that looks like a supernova signal, we know to look up in the sky and expect to see the actual supernova in a matter of minutes after that.
So the neutrinos precede the visual of the nova?
And yes, they do. And it's neutrinos don't travel faster than light. It's not that sort of thing. What's happening is when the supernova is collapsing, there's all these nuclear reactions going on, but the supernova is so dense that the photons can't escape. The supernova is essentially opaque to the photons, to the light, but neutrinos travel right through that stuff. So all the neutrinos that are created, they actually get out before the light does. And then, of course, it explodes and the light goes everywhere. But we've got the neutrino signal telling us, hey, something's about to happen, and then we can look up and see it.
Wow.
Yeah, it's exciting stuff.
It actually is. I didn't know that that when the stuff was collapsing like that other stuff was already leaving and on its way.
Yeah.
So what you're saying is when you guys detect a large amount of neutrinos, you're immediately looking up for visual evidence of supernovas?
Yes, absolutely. In fact, this happened in 1987 when there were just there were 2 neutrino detectors on Earth that were really sensitive to this sort of thing. They witnessed a signal, weren't really sure what was going on, and then supernova, what we called 1987A, was seen in the night sky. And we learned so much from that one supernova that it spawned something like 1,000 publications just on the few seconds of data we got from that supernova. In fact, I think they were still publishing papers on that data as of 2 years ago. There may still be some in the works, I don't know, but just 2 years ago, one came out and it was actually titled Yet Another Paper on 1987A. And since then, we've built a lot more neutrino detectors for different projects, and most of the big ones are involved in they're involved in something that I think is called the Supernova Early Detection Network. They're their detectors are actually set up to automatically go through a call list of people if they sense something that looks like a supernova that's about to go off. So that's a network that's already in place. Unfortunately, since 1987, we haven't had a supernova inside our galaxy, one that's really useful.
So how often do they think that supernovas happen in our galaxy?
About once every 100 years.
Wow.
Yeah, and so it's
Interesting.
Yeah.
So we had our shot, and it's going to be a generation. Or?
Fortunately, it's not on a schedule. So we probably will see one.
Less reliable than Halley's Comet.
No auto notifications? What are we going to do?
Well, the neutrinos hopefully will provide that.
Yeah.
There we go.
But you're going to have to be on the ball. You're going to have to be real quick with that telescope.
So we got another...
Oh, okay. Go ahead, Justin.
I got it. The Burin asked the question, so can you tell us about the neutrino detector that will be set up at the lab in the next 10 years?
Good. I was hoping to have a chance to talk about this because this is really big as far as Sanford Lab is concerned. I talked about the 22 projects that we have going on, and those 22 projects are doing incredible science, and we've already discovered some pretty incredible stuff underground. But in the next 10 years, we will be installing the United States' single biggest scientific experiment at Sanford Lab.
Wow.
And that's going to be a massive neutrino detector called DUNE, which stands for Deep Underground Neutrino Experiment, part of LBNF, cool. Which is the Long Baseline Neutrino Facility. We'll be working with Fermi Lab just outside of Chicago to make all this work. So this is basically what's going to happen. Fermi Lab has a giant accelerator. If you've ever seen pictures of Fermi Lab, they have the fields with a circle kind of drawn in the ground. They have an accelerator where they accelerate protons in a circle. They will generate a neutrino beam from that accelerator, and that neutrino beam will be pointed through the Earth to us in South Dakota, nearly 1,300 kilometers away or something like that. Those neutrinos will be picked up by our massive neutrino detector. It's a detector that will contain 13 million gallons of liquid argon. And what we're looking for is specifically how neutrinos change as they travel. This is one of the weird things about neutrinos.
Wow!
As they as neutrinos come to us from the sun, as they travel through matter, they actually change what type they are. There are three types of neutrinos that we know about. We call them the electron neutrino, the muon neutrino, and the tau neutrino. And it turns out if you create an electron neutrino in one spot and then send it to another spot, it may not necessarily be an electron neutrino when it shows up.
Wow.
It could be something entirely different. It's the same neutrino, but it's mutated. It's changed. And we really need to understand that because that's a massive part of our universe. So Fermi Lab will be shooting this neutrino beam through the Earth to us at Sanford Lab, and we'll be understanding, or hopefully understanding, how it changes as it travels through the Earth. And that's going to be, it's essentially going to be America's flagship science project for the next 20 years. It's going to be incredible to be part of that.
That's a collaboration between Sanford, Fermi Lab, and CERN, correct?
Yes, CERN will be involved, but it's not just us. It's over 100 universities.
Wow.
It's over, last I heard, it's over 700 scientists internationally. It's not just American institutions, but it's European and Asian institutions. We're going to have, I wish I had the stats in front of me. We're going to have a lot of people involved in DUNE, and it's going to be really a worldwide collaboration, and it'll be the first worldwide collaboration on this scale that's on American soil.
So one of the questions was, how will you determine when the changes occurred?
Mathematically is the short answer to that one.
See, that's unfair. You can just keep saying that, and we can't challenge you.
It's a pretty good get out of jail free card.
Yeah, it is.
We actually already we understand quite a bit about how the oscillations occur already, because we've been running for years a similar experiment that shoots a neutrino beam from Fermi Lab to the Sudan Underground Lab in northern Minnesota.
That's
and they have.
Is that up in Hibbing, Minnesota?
It is. It's actually very close to Hibbing, probably 40 miles away.
Okay.
And it's an experiment that has taught us quite a bit about that oscillation, but by that's only 700 kilometers away. By extending that distance quite a bit more, we'll understand quite a bit more about that oscillation, and even more, we'll understand a totally different problem about neutrinos, which is how much do they weigh? We know that they have a mass, but we have no idea what that mass is. They're so incredibly light that none of the methods we've used for measuring masses of other particles has worked at all. So we have to devise totally different methods for understanding the mass of the neutrino, and this extra length on the baseline, this extra length between Fermilab and us, will actually clue us in on that weight. But as to the original question, telling where they change, it's not that simple is the problem, because it doesn't change at one point. It doesn't go from electron neutrino to tau neutrino like that. In fact, anytime you've got any neutrino, it exists as a superposition of all three. It's all three in different percentages. So it may be 90% an electron neutrino and 5% a tau neutrino and 5% a muon neutrino. And when it goes somewhere else, it's a slightly different percentage. And at any given time, it's all three. It's just hard to find out how that oscillation occurs. So there's no one point at which it changes from one to the other.
So Mark, what project are you currently working on, or are you jumping into now?
Well, I'm working on a project called CASPAR, which you're going to have to give me a second here, because the acronym is a bit it's convoluted. It's the Compact Accelerator for Astrophysics Research. Basically, it's a tiny accelerator, just like CERN is an accelerator or Fermilab is an accelerator. This is an extremely scaled down accelerator so that it fits in a single room, that we're using to actually create the same conditions that are inside the cores of stars to understand how they create the elements of life. You've probably heard before the famous Carl Sagan quote that we are all made of stardust.
Right.
He was talking about how in the Big Bang, in the beginning of the universe, helium and hydrogen was created in abundance, but there was really not much else created, which is a bit of a problem because human bodies are composed mostly of oxygen and carbon. So we wouldn't have a place to exist. We wouldn't be able to exist unless there was a way for the universe to create all these heavier elements. And the way it does that is in the core of stars. And we understand that happens, but we don't understand all of the hows yet. So underground, we'll be using a beam to shoot mostly alpha particles or protons at a target of oxygen or nitrogen or neon, and create new elements, just the same way that the elements are created inside of stars, to try to understand how those processes go on in the universe. And it'll help us put limits on stuff like how many other planets out there could life exist on, and how long will this period of the universe where life could exist at all survive, and really what's the ultimate fate of all the elements in the universe. It's questions like this that we get to answer. But ultimately, of course, I joined it because I get to tell girls that I make stars underground for a living, and that's pretty cool.
That's awesome.
Best pickup line ever, possibly.
Has it worked for you so far?
I did get one date off of that line once.
There you go.
Yeah, I'm pretty pleased with it.
It's the old 1 out of 100 theory, right? You say it 99 times, you get that one. That's all
Makes it viable.
That's awesome. So what are the, when CERN went live, right? I'm going to skip to CERN for just a second. But when CERN went live, you had everybody freaking out because they thought they were going to create black holes that were going to suck up the Earth and or whatever. I guess they were watching wormholes that were going to, I don't know, move people to Venus. I don't get it, but the
we're going to be invaded.
So compared to CERN, how much power is going to be pumping through your guys's accelerator? I know you said it's a smaller accelerator where CERN is like 26 kilometers or something like that across or whatever it is, but what are you guys going to be able to do with yours?
Almost no power requirement at all. I haven't checked the exact cabling we have going in there, but I'm pretty sure most of it plugs into a 120 volt outlet. That's actually the interesting part for us, because CERN has to have a lot of power because they're trying to recreate really highly energetic collisions like the Big Bang would have had. Specifically trying to create the lowest energy reactions that we possibly can. Because in the center of a star, we don't think about this much, but the interactions on a nuclear scale that take place inside the center of stars are actually incredibly low energy compared to all the other collisions that happen in the universe. I'm not saying it's not, high energy compared to what happens on an everyday scale.
Is that because of its consistency there?
Or that certainly has something to do with it. Slow and steady wins the race. But ultimately, it's because the center of a star may be 100 million degrees or 100 million Kelvin. As far as the universe is concerned, that's not particularly hot. That's not very energetic, really, at all.
What do you mean?
I see some confused faces.
Yeah, what do you mean that's not very energetic? I mean, okay, obviously, so when...
It seems energetic to us.
Right. Well, I mean, I get it. I think when something goes nova, that probably creates a lot more heat, a lot more energy, stuff like that. But outside of that, how the hell more energetic do you have to get than 1 million degrees Kelvin?
Well, I don't want to suggest
I don't know what 1 million degrees Kelvin is. So for anyone that does,
pretty damn hot.
Yeah, it's pretty close to 1 million degrees Celsius. You're on your own if you want to figure that out in Fahrenheit. I can't do that for you. But it boils down to, I don't want to suggest that CERN is creating collisions that are incredibly hot, but rather they're creating collisions where the two particles are aimed at each other head on. So all of their energy is directed into each other. Whereas in a thermonuclear reaction, for instance, all of the energy isn't directed head on. You've got particles going every which way, and only every now and then does one actually connect with another one and actually, create a reaction. That they're creating in CERN, they're creating one tiny, tiny spot that has an energy of probably several billion degrees, but we can't really call it a temperature because you don't have a temperature when you only have two particles. Okay. Temperature is something that only applies to systems of a lot of particles. So the center of the sun has, 100 million degrees, but the particles are going everywhere, and most of the energy is wasted in just traveling around, and only occasionally do two actually meet up and then create a product that we're interested in studying. I don't know if I actually explained that right or just went off on a tangent, but it felt good.
Well, that's good. Felt good to put it in perspective, I suppose. So you guys you're using the lowest power settings possible that you can to generate these reactions. Outside of looking at those low energy create or low energy discoveries, what else do you expect to be able to do with this accelerator?
Well, it's really a single-use accelerator. We intend to use it for this single purpose.
Okay.
But it'll take us a long time to gather data, and there's also a lot of different reactions we want to check. So we expect to run this accelerator in its current mode for probably 20, 25 years.
There's a question about how old the accelerator actually is.
I recognize the username. That's actually a scientist I'm working with, and he's trying to embarrass me. Because our power requirements aren't particularly high, we can live with an accelerator that doesn't use a lot of power. So we're actually using an accelerator from the 50s. That it came to us from Notre Dame, and we're actually working with Notre Dame on this particular experiment. But the accelerator part itself is an old bell with it's really just a Van de Graaff generator on the inside of it, and it's about 50 years old. But when you're doing really low energy research, anything really bigger, anything newer is going to screw us up. It's going to give us too much energy.
So if it's not working, you seriously just have to go and check and see if it's plugged in.
Yeah, actually, that's not just this project though. That's a lot of physics. You'd be surprised at how many problems are solved by doing that.
I guess I like my science experiments ungainly large with electric bills in the hundreds of millions of dollars every day. It's kind of, I mean, it's cool, but it's kind of disappointing. You know, you kind of expect you hear particle accelerator, and you're thinking, okay, 99.9% speed of light. Let's smash some shit together and see what happens, right? And this isn't like that at all, which is kind of contrary to what we think of when we hear the term accelerator.
Yeah, and that's because we're looking at incredibly low energy collisions, incredibly low energy reactions. That's why we have to go underground. If we were doing experiments with the energy of CERN, we could do it on the surface and not care, because any interference we would get from cosmic rays or cell signals or radiation signals from people walking around, those would pale in comparison to the signal we would be getting out of our incredibly energetic accelerator. But because we have to look at the low end, the really low energy frontier, we have to go underground and block ourselves from all the stuff that's, louder than the signal we're looking for. So that's why it has to be a mile underground. And this sort of work has never been done before underground. So we will be able to explore territory that no one's ever had a chance to look at before.
So how much? Another question here was, how much radiation does the accelerator emit?
I saw that, and I'm afraid I don't actually know off the top of my head how much we will emit. To put it in a human scale, I don't expect that it will be anything harmful to the human body. I expect that you could run this thing and be in the same room at the same time. That being said, our safety protocols, of course, wouldn't allow that. We have giant lead doors between us and the accelerator when it's running. But I've worked with accelerators like this before, and the amount of radiation they actually emit is not on a seriously dangerous level. I wish I could give a more mathematical answer to that, but I haven't gotten far enough into it to actually run the numbers. Okay,
I'm assuming that the Burin is the geologist that you were talking about that eat rocks.
The Burin is actually a dark matter physicist.
Okay, all right.
The guy is seriously smart, even though he's trying to trip me up.
Because he said, who doesn't want to know about the radiation levels of a word that starts with an A and
amphibolite and rhyolite?
Amphibolite and rhyolite. Yeah, he was the one who was asking before about the types of rock, and he's right. They are amphibolite and rhyolite in that area. I don't know what those words mean, but I recognize them from being underground. I know that one does have a uranium and a thorium content, which is of concern to really low, really sensitive experiments, but it's something that we're able to block out locally. So that may be worth discussion right there. Radiation is it's scary to talk about radiation, but the truth is, it's part of everyday life. Radiation is all around us. I mentioned before the human body is really, really radioactive, and it is. The human body is constantly emitting gamma rays and alpha particles and beta particles. It's just part of our makeup because the human body has uranium and it has thorium and it has a heck of a lot of potassium in it, especially if you've eaten a banana recently. The type of experiments that we're doing underground, particularly the Lux experiment and the Majorana experiment, they're so sensitive to radiation that even the presence of a human body, which like I said, is radioactive, but not to the point where it would damage anyone's health, that would destroy our experiments because we're just that radioactive. So when we go underground, of course, we have to go to great lengths to make sure that we don't have radiation in our area. So we start by going underground and blocking ourselves from radiation on the surface. And then we have to block out all the local radiation, like the amphibolite and the rhyolite has some radiation in it. Cinder block has a ton of radiation in it because the stuff they make cinder block out of has typically high concentration of uranium and thorium. So we use typically lead shields around a lot of the stuff we're using because lead blocks out most radiation. Or we use water shields in the case of Lux because water is really good at blocking radiation. But then we also have to make sure that the material that we make our detectors out of is itself radio quiet. It doesn't have a lot of radiation in it. So there's a lot of consideration that goes into making this stuff. And it's funny when you get down there that you have to think about the fact that the human body is one of the biggest sources of radiation.
Do you have any experiments where you use both water and lead?
Let's see. We don't have any right now at Sanford Lab. I have worked at another lab where we had a very sensitive experiment that used a very big lead castle around the experiment, and then around that was a vat of water.
Okay.
Occasionally that helps, but typically it's overkill. Simply because dealing with lead bars inside of water is just a mess. You typically go one way or the other.
That's really cool. Well, we're actually about a half hour over our time here. And I guess I really got to say, Mark, we really appreciate having you sitting here talking with us tonight. And the great job that you're doing at Sanford, the entire Sanford facility really is just cool to talk about. And we really enjoyed it. Having you talk to us about gravitational waves tonight was mind-boggling beyond belief because we definitely learned something. I think anyone who was sitting on here learned something, and we really appreciate your time.
It's quite a treat.
Well, it's been a pleasure. Give me a call anytime. I'd love to talk to you guys more.
Yeah, great. And
you definitely have an invitation to come back in a non-scientific capacity and join us for another show on another subject.
Oh, excellent! That sounds like a lot of fun. I'd love to do that.
It'll probably be Star Trek, though. Just to let you know, you might want to start watching.
That's a weak field for me, but I'm willing to work on it.
Well, if we're going to use gravitational waves to help us with warp drive in the future, we're going to need you to brush up.
Just pick on him about the red matter.
Yeah. Michael and Kuda, they were really good at putting it together. Yeah, we didn't talk about red matter, and that's going to be a good topic for later. But you guys, I want to thank everyone for stopping in and watching the show tonight. I know that we had a blast. Mark, thanks a lot for coming in. We are the Junkie Chunks. We are live every Thursday from 9 p.m. Central Time to typically 10 o'clock Central Time, but sometimes we go over like tonight when we have great guests and a great topic to talk about. Next week, make sure you join us next week, because next week we're going to be digesting or dissecting probably both. Digesting and dissecting the results from Super Tuesday. We're going to go a little bit political next time.
Your Rolaids.
Bring your Rolaids and some alcohol, because we're definitely not going to pull any punches talking about both sides of the political equation. But thanks for tuning in. Again, we're the Junkie Chunks. I'm Dylan Walter. I've got Tony Sisson, Justin Batts here with me. The special guest tonight was Mark Hanhardt, and you guys have fun. Thanks a lot.
Before we go,
we're still going.
I wanted to say one thing. I just wanted to correct something I said earlier. I've looked it up. the neutron star question, I was totally wrong about the masses. They are typically very small. They're typically between 1 and 3 solar masses. So
very cool.
That's why Vuk, the scientist you spoke to on LIGO, said that neutron star collision would have to be much, much closer.
Okay.
So I was totally wrong on the masses there.
Wow,
I hated to interrupt the ending of the show, but I wanted to make sure that was out there.
Thanks for clarifying, though. That was really cool.
Don't worry, we'll edit that out. So
very cool.
All right. Again, everyone, thanks for watching, and have a good night.
Bye.
Thanks.